infrared spectroscopy. So here we have different sources and different detectors than we have for UV vis, and that's because a lot of the things that work for UV invisible light don't really work very well for IR. So we have to use sort of a novel, sort of a tricky strategy for measuring infrared radiation. So basically, you can use sources like a silicon carbide glow bar, which is by far the most common. You can also get lasers that will excite in the IR. And then for detectors, you need something that will create a potential difference or a potential difference voltage or current as a result of being exposed to heat. And so you can use things like a thermocouple, which is also used in many thermostats. You could use a pyroelectric material that changes polarization as a function of temperature or getting heated up. You can use something that's photoconductive, so a change in conductivity based on exposure to IR radiation, or maybe even a photovoltaic. And another thing that doesn't work very well for IR is a monochromator. Mirrors of the type that we have seen in a monochromator really don't work very well with IR. Like you could put a hairdryer into a monochromator all day long, and you would never get a single wavelength of IR electromagnetic radiation out. So we have to use something tricky called an interferometer, which was invented by Michelson in 1880. It was also used in the Michelson-Morley experiment that showed the speed of light was constant, which is very cool. Like these people like it's fascinating. Anyways, basically what you have is you have an IR source, so like a glow bar, and that radiation goes into the instrument. It gets split into two different beams. One goes to a stationary mirror and comes back, so it's a fixed path length. And then this other part goes to a moving mirror. So it moves constantly back and forth, back and forth. It's always moving when you're making measurements, traveling. And so the path length that light travels to the moving mirror and back is different from different from the distance it's traveling to the stationary mirror and back. So they are somewhat out of phase when they come back together. And mind you, this is many wavelengths of infrared radiation that are coming from the source. So it gets a little bit complicated when you think about it like that. So I think about it as being one wavelength, and then sort of try to scale it up, but it kind of blows my mind. So you have the radiation coming here, and then so because it's a different distance, then you have deconstructive or constructive interference of the waves of the electromagnetic radiation as it's recombined when they both have gone to the mirror and either mirror and come back, and then both that recombined wave or photon goes and interacts with the sample, and then it's detected. And one of the important pieces is that you need to know exactly where this moving mirror is at all times so that you can figure out what the detector is detecting and how those different waves will be interfering with one another. So you need to know the difference in the distance traveled from the stationary mirror and back as compared to the distance traveled to and from the moving mirror. And you do that by using a laser that can tell you exactly how far it is to the moving mirror and back at all times. Alright, so what's important to know is that you are getting simultaneous detection of all wavelengths. So it looks like this. It's called an interferogram, and it looks like this. And this is in voltage at the detector. And so this is basically the spectrum of the source minus the sample spectrum. And so you use a bunch of fancy math called a Fourier transform, and we're not going to talk about the math for that. There's an app. You can do fast Fourier transforms of all kinds of things using apps, which I think is very fun. But basically you can deconvolute the source and sample spectrum at all these different wavelengths as long as you know the position of the moving mirror, and you're able to come up with a spectrum that is percent transmission on on the y-axis and wave number in inverse centimeters on the x-axis. And this is a pretty bad representation of an IR spectrum, but you know, you get the idea. And I'm sure that you guys are getting, or I suspect that you guys are getting exposure to at least the spectrum and how to identify the different vibrational modes in the spectrum in your organic class, because it's often used to identify and try to understand organic molecules. Although it can also be used for the detection of minerals. I haven't done that. So let's talk for just a second about sample prep, because if you put your sample in water like you would for a UV vis, and then put it in the IR instrument, you're unlikely to get a sample. Your sample spectrum is going to be all swamped by an OH stretch or the OH vibrations from the water. And so you can either disperse it in mineral oil, or you can press it into a KBR pellet, where you take like 1% sample, 99% KBR, mix it up, and then press it into a pellet. KBR optics are actually those are good. KBR is a good sort of medium to disperse your sample in, because it's not very IR